In computer science, a low-level programming language is a programming language that provides little or no abstraction from a computer's instruction set. Architecture, commands or functions in the language map closely to processor instructions. Generally, this refers to either machine code or assembly language. The word low refers to the small or non-existent amount of abstraction between the language and machine language. Because of this, low-level languages are sometimes described as being close to the hardware, because of the close relationship between the language and the hardware. Architecture programs written in low-level languages tend to be relatively non-portable. Low-level languages can convert to machine code without a compiler or interpreter. Second-generation programming languages use a simpler processor, called an assembler, and the resulting code runs directly on the processor. A program written in a low-level language can be made to run very quickly, with a small memory footprint. An equivalent program in a high-level language can be less efficient and use more memory. Low-level languages are simple, but considered difficult to use, due to numerous technical details that the programmer must remember. By comparison, a high-level programming language isolates execution semantics of a computer architecture from the specification of the program, which simplifies development. Low-level programming languages are sometimes divided into two categories: first generation and second generation. Machine code. Machine code is the only language a computer can process directly without a previous transformation. Currently, programmers almost never write programs directly in machine code, because it requires attention to numerous details that a high-level language handles automatically, requires memorizing or looking up numerical codes for every instruction, and is extremely difficult to modify. True machine code is a stream of raw, usually binary, data. A programmer coding in machine code normally codes instructions and data in a more readable form such as decimal, octal, or hexadecimal, which is translated to internal format by a program called a loader or toggled into the computer's memory from a front panel. Although few programs are written in machine language, programmers often become adept at reading it through working with core dumps or debugging from the front panel. Example: a function in hexadecimal representation of 32-bit x86 machine code to calculate the nth Fibonacci number. 8B542408838FA0077006B8000000 C383FA02776B8010000 C353BB0100000 C9010008DO41983FA03768BD98BB84AEBF15BC3 assembly. Second-generation languages provide one abstraction level on top of the machine code. In the early days of coding on computers like the TX0 and PDP-1, the first thing MIT hackers did was write assemblers. Assembly language has little semantics or formal specification, being only a mapping of human-readable symbols, including symbolic addresses, to opcodes, addresses, numeric constants, strings and so on. Typically, one machine instruction is represented as one line of assembly code. Assemblers produce object files that can link with other object files or be loaded on their own. Most assemblers provide macros to generate common sequences of instructions. Example: the same Fibonacci number calculator as above, but in x86 assembly language using MASM syntax. Fib, MOVEDX, especially +8, CMPEDX, 0 yarat FMOVEAX, 0 retatit, CMPEDX, 2 yarat FMOVEAX, 1 retatit. Push EBX MOVEBX, 1 MOVECX, 1 atit. LEAX, EBX plus EC, CMPEDX, 3JBE at FMOVEBX, ECX MOVECX, EAX DEC EDX JMP at BATIT. POP-EBX in this code example, hardware features of the x86 processor are named and manipulated directly. The function loads its input from a precise location in the stack and performs its calculation by manipulating values in the EAX, EBX, ECX and EDX registers until it has finished and returns. Note that in this assembly language, there is no concept of returning a value, the result having been stored in the EAX register. The ret command simply moves code processing to the code location stored on the stack, and it is up to the author of the calling code to know that this function stores its result in EAX and to retrieve it from there. x86 assembly language imposes no standard for returning values from a function. It is up to the calling code to examine state after the procedure returns if it needs to extract a value. Compare this with the same function in C. Unsigned int fib if return 0, else if return 1, else int a, b, c, a equals 1, b equals 1, while c equals a plus b, if return c, a equals b, b equals c, n. This code is very similar in structure to the assembly language example, but there are significant differences in terms of abstraction. While the input is loaded from the stack, its precise position on the stack is not specified. The C compiler calculates this based on the calling conventions of the target architecture. The assembly language version loads the input parameter from the stack into a register, and in each iteration of the loop decrements the value in the register, never altering the value in the memory location on the stack. The C compiler could do the same or could update the value in the stack. Which one it chooses is an implementation decision completely hidden from the code author. The local variables a, b and c are abstractions that do not specify any specific storage location on the hardware. The C compiler decides how to actually store them for the target architecture. The return function specifies the value to return, but does not dictate how it is returned. The C compiler for any specific architecture implements a standard mechanism for returning the value. On x86 architecture, the compiler returns the value in the EAX register, as in the assembly language example. These abstractions make the C code compilable without modification on any architecture for which a C compiler has been written. The x86 assembly language code is specific to the x86 architecture. Low-level programming in high-level languages. In the late 1960s, high-level languages such as Place, S, Bliss, BCPL, Extended Elgal and C included some degree of access to low-level programming functions. One method for this is inline assembly, in which assembly code is embedded in a high-level language that supports this feature. Some of these languages also allow architecture-dependent compiler optimization directives to adjust the way a compiler uses the target processor architecture.